Hey everyone, welcome. You know what is the fastest page you can actually create? It's really a blank page. Okay, that is the fastest page you can create. But unfortunately, that's not what your end users want. Okay? And the last time I checked, pages are becoming bigger. They're actually becoming more diverse content. And your customers are expecting immediacy. On that note, welcome to the presentation on milliseconds matter. How do you design for low latency? No presentation on performance is actually valid, in my opinion, until you actually discuss the priorities for a web application. In my opinion, the priorities are in this order. Tight security is the #1 priority for your web application. Okay? High availability comes next, and then comes performance. I'm actually explicit about that priority, guys. And there's lots of presentations on security and availability in this conference. I'm not going to discuss that here, but there's a presentation on building anti-DDoS resilient architectures at 5:30 today. I encourage you guys to go watch that. In terms of availability, the right way to actually measure availability is from the client side. Okay? If you're building a web application, you have to know how your end users are perceiving your availability. This is actually measurement from a third-party provider. We use Sidexis for measuring our application's availability. And what you can see here is that there are lots of providers out there, and they have occasional dips. And even a 0.5% dip in availability, and this is the United States, when you have millions of users, has an impact on your application. Now, why does milliseconds matter? And there's a lot of research on that, lots of very detailed research. And what I'm going to be presenting is a couple of examples of research that has been conducted in the industry today. This data is publicly available, actually. This is research from Bing, Microsoft Bing. What they did was they actually induced latencies of the order of 50 to 2,000 milliseconds. And they actually observed user behavior. They observed user behavior on multiple dimensions. The gist of this is that about a 1% reduction, a 1% introduction of latency actually reduced their revenue per user by about 2.8%. That's a significant amount. There's lots of other data. I encourage you guys to go read that paper as well. Similar studies were done by Google, where they introduced latencies on their server side for search results. And the interesting part of that experiment was that a 400 millisecond latency introduced long-term side effects. And what that meant was, after they turned off the experiment, they still observed that their users did not have the same experience about 5 weeks after they turned it off, which means they saw about long-term effects of 0.21%. That's actually pretty important to understand. What that means is, when you introduce latencies into your web tier, those effects actually have long-term side effects. There's also neuroscience research that has happened in this area. In fact, they've actually figured out that humans typically react to visual stimuli in about 150 to 200 milliseconds. Okay, there's lots of research in that area as well. Now, what does that mean? Does that mean we have about 200 to 400 milliseconds to play with? Well, that's great. Let's go home and let's actually make our applications slower by 200 milliseconds. That gives you a lot of capability to add more features in. That's not true, because remember I talked about how pages are becoming larger and they're becoming more diverse. An average web page today has about 100 objects, and it's about 2 megabytes in size. And when you see that, when you take the 200 milliseconds and you amortize it across your 100 objects, you don't have a whole lot to play with. And that is why milliseconds of latency do matter. Okay? Now, before you embark on trying to go and make your web applications low latency, the first thing you need to invest in is telemetry around it. You need to have detailed telemetry on where your latency is being observed, what parts of your application can you improve on. And there's lots of commercial products out there that actually measure this for you. It starts all the way from data center and backbone measurements. Those are the simplest ones to set up. They're low in terms of accuracy. I recommend that you do not rely on just that. They have a place. But if that's all you rely on to understand your end user behavior, you're not really getting a good, accurate picture of what your end users are experiencing. And the reality is your end users are not sitting in data centers, so any measurement from data centers is kind of pointless. Okay? You go up the stack, There are last mile measurements, which are slightly better, still not really representative of your user experience. Go further up the stack, and you have synthetic real-time measurements. Synthetic real-time measurements mean that you put web bugs on your web pages, which are not web bugs that are owned by you, but they're measuring latencies from your end user's perspective. So surely better, gives you a good idea of where, which networks are slower, which networks are faster, what your latency measurements are by regions and by specific ASNs. So it's surely better. The right way, or the most complicated way really to implement it, is real user measurements of architecting your web pages. It's harder to do. It has a lot of benefits. And I encourage you guys to actually look at either synthetic measurements or real user measurements. In fact, anecdotally, there are so many conversations I have with many customers where they come and say, oh, my web application has 5 millisecond latency. And I tell them, that's not real. Okay, when you really go look at, dive into what your first byte latencies are and what your page load times are, you rarely get anything of the order of 5 milliseconds. Okay? So a little bit of under the covers, like what does it take for us to actually develop low latency services for you? Okay? And what I'm going to actually talk to you about is how we evolved in one of our services, which is actually built around providing customers high availability and low latency. Okay? I'm going to peel the onion. I'm going to tell you what our evolution was and explain to you what did it take for us to build those services on your behalf. Okay? The one I'm going to talk about is CloudFront. And if your application is just relying on a single instance sitting in anywhere in the world, the speed of light is just too slow for you to provide a good low latency experience. So you don't have a choice but to rely on services that actually spread this content across multiple locations. Okay? The second important part of it is what I'm going to talk about in the remaining part of the presentation, which is about our routing algorithms. So I'm going to tell you how we actually evolved in CloudFront in building our routing algorithms such that we can optimize latency for viewers. So the first thing we started with was anycast routing. So we looked at our network and we said, well, briefly, you announce your IP space from multiple edge locations. You rely on the internet to actually associate a specific user to an edge location by following the shortest hop path. So this relies on BGP and network business policies. And here's what we found. So here's a schematic. You have an end user in Singapore, and you have 3 stars that actually represent our edge locations, Singapore, Hong Kong, and Tokyo. And what we did was, we said, OK, let's announce our name servers from all these locations, and we did a trace route. Okay? And here's the important part of the trace route. So we trace routed to our name server from our end user network in Singapore. And what that trace route showed you was it went through Singtel, which is the provider for that particular end user, and it went all the way to Tokyo first. So the internet is actually just not a simple ball of connections. It's actually a complex network of different policies, and it's governed by all these different providers who have financial agreements. And so it's not straightforward to say, well, let's just use Anycast and actually route customers to the right location. So a meaningful set of our customers sometimes were assigned to locations which are outside the country, and even sometimes even outside of continents. Okay? So you said, oh, great, that's easy to fix. Let's actually move on to geo-based routing. And what we did there was we said, well, let's look at the network, and let's associate IPs with geographies, and let's associate them with the right edge locations in those geographies. Simple enough. So here's a schematic of that. Again, the same user, the Singapore viewer network, the resolver that they use, our edge location in Tokyo and Singapore. So the DNS query is for d123.cloudfront.net. Goes to their resolver that they use. The DNS server responds back, and now we used some CNAME trickery where we said, well, if you ask for d123, we're going to give you back d123.sin.cloudfront.net. Sure enough, the resolver gets d123.sin.cloudfront.net, makes a request to that specific DNS server, gets back an IP address, makes a TCP connect, goes to a Singapore location. Okay? Happy? Same schematic again. And now we did a trace route again for our Singapore name server. And here's what we found. We found that we exited Singtel as before. Then we went all the way to Hong Kong, and then came back to Singapore. So to reach Singapore edge location, we were going through Hong Kong. Okay? That's what we did. So we said, well, that doesn't make any sense. How do we fix this? We can keep going and fixing this whack-a-mole-like approach. And the network that we actually run, we can't afford to do this. We can't afford to be fixing one-off things like that. We have to build automation around it. That's when we thought about latency-based routing. Okay, this was many years back, and now CloudFront is a latency-based routing system. And what we said is, what matters to customers is not the number of hops. Customers don't care about geographic proximity, and geographic proximity, we proved, is not the same as latency proximity. And we said, let's just route based on latency. So how do we do that? So the way we do that is by gathering billions of measurements of actual end-user latencies to all our edge locations. And this is a learning system that we actually built. We said, well, let's learn about latencies to all our edge locations, and let's route based on latency. So here's what it did, the same schematic. So we have a routing engine that actually continuously gathers latency data from all these different edge locations for real users, and it creates two mappings. It creates a mapping between our viewer networks and our edge locations and calculates those latencies and continuously learns about it. Then it creates a mapping between the viewer networks and the resolvers that they use. Okay? So here's how that works. So the Singapore user, again, makes a request for d123.cloudfront.net, makes a request to our DNS resolver. Our DNS that DNS resolver. The DNS resolver then anycasts it to Tokyo. Tokyo then looks at our mapping and says, the better place for you is really Hong Kong, and I'm going to return back to you 5.6.7.8. And that's how we actually route Singapore users to Hong Kong, and we learn about latencies when we actually route them to the right location. Now, that was fine and dandy until about last year, or this year, actually. And what we found was that there was a prevalence of open resolvers, like OpenDNS or Google Open Resolvers, which means our routing, which is based on just resolvers, was suboptimal in some cases. So we said, what do we do in that case? And then introduce an option called eDNS0. And what eDNS0 is, it's basically a client subnet extension to DNS. And what that does is, as part of the DNS request, you actually get a portion of the client's IP, typically a /24. And we already had our mapping for all these viewer networks and their latencies to edge locations. So we said, we'll use the client subnet, if available, to route them to the right location. And that's what we did. We launched this in March of this year. In fact, quite surprisingly, the first graph there, 20% of our responses today are for eDNS0 option. It's actually quite impressive. It's quite telling as well. And here's an example of a specific network. This is in Germany, where we look at our P90 first byte latencies, and they actually dipped significantly, went from all the way from 150 milliseconds all the way to 10 to 12 milliseconds in latency. Okay? That was a pretty good success for us to actually really go and look at this network and understand what was happening in terms of our routing and design around it. Okay? So why am I talking about all of this, and what does it matter to you? Well, what I'm trying to impress on is trying to build applications that are low latency requires a significant amount of operational focus. It requires you as operators to go look at the data, understand what the data is saying, potentially do some manual changes to understand what the implications of it are, and then go back and really introduce operational systems and automations around it. Okay? We had to build these kinds of automations so that we can scale our network. That's a lot of heavy lifting. Does it really mean that everyone in this room is going to go back and architect your applications for it, learn about it? It's a lot of heavy lifting for what you want to deliver to your end users, and you should be focused on delivering those to your end users. That brings up to the next part of the presentation. I'm going to introduce John, is how do you use the services that we've actually built such that you can take advantage of the improvements that we've done over time. Okay? Thank you very much. John? Okay.
Okay, so let's see. I think this moved on to the next presentation here somehow. Okay. It's actually not advancing. Okay, there we go. Thank you. Or no? Yes. Okay. Sorry about that. All right. So, we heard a lot about the engineering effort that the CloudFront team went through to get you the system that you could leverage to really get great performance out of your applications. Now what I want to do is see how you can actually implement that, right? And to do that, I want to start with a baseline application and go through a series of optimizations and see what we can do for page load times. I'm going to do it basically in an around the globe kind of fashion. All right, so first thing we're going to start off with is what does a typical web page looks like, right? What is it that, what are the types of content on a typical web page? So typically, the baseline that I want to start with is the Amazon Health and Beauty site. I just thought this might be relatively representative of the types of sites that you guys might be developing. It's an e-commerce kind of application, clearly, and this seems pretty broadly relevant. So if you look at this web page, there's two kinds of content on it. There's pre-generated content, like images, CSS, JS files, and then server-generated content. This is things like the page itself and any API calls that are responded to from AJAX requests. So if you take another view of that same application, this is using the Chrome developer tools to just generate a waterfall graph here. There's other developer tools out there from Firefox or Firebug, whatever your favorite tool is. But definitely make sure if you're thinking about how to optimize a page from a performance perspective that you are using some sort of waterfall chart. Extremely helpful. But if you look at it from this view, you'll see that this page has 108 requests and about 2.8 megs of data downloaded, just to render this one page. One page load takes that many requests and that amount of data. And you can see the breakdown in the number of specific objects. And this very tightly matches up to the numbers that Prasad mentioned earlier. All right, so since I don't have the source code for the Amazon Health and Beauty application, yes, I work at Amazon, no, I do not have access to that source code, I had to refactor this site, right? I had to create a mock-up of this. I want to use this as the baseline, but I don't have the content itself. So what I did is save out all the static assets, comment out the JavaScript so I'm not getting kind of JavaScript errors, and replace the body content by a shuffled number list. I did that so anytime that I'm refreshing a page, I can know that I'm not looking at a cached version, right? I just wanted something to give me a little bit of dynamic effect to content that I'm generating on the server. All right, so I'll show you very simple. This is kind of loosely based on the Flask, Python Flask framework. I had to make this into, shorten it quite a bit so it could fit on one slide, but it's roughly what I was actually running throughout these tests. So I have a function to do getting that random or shuffled number list. I have a variable called static, module level variable called static, which is going to point to where the static content lives on the server. So in this case, it's going to be static slash, right, and then whatever the name of the static file is. And I have two functions, one called root and one called AJAX. The root is just going to render a template. We'll take a look at the template in a second. And insert 5,000 random number or shuffled numbers for the body content. And AJAX is going to just return the roughly whatever number of numbers need to be rendered via a query string parameter. So a very simple kind of app logic, no database, nothing like that. I'm really looking at how we can improve, mitigate the impact of latency or an application, not within the application itself, to things like a database. And then we look at this template. All right, so here again, very simple, kind of redacted version of the template here, but we had what I have is 100 or so of those first lines, which are links to the static assets, the image files, CSS, JS, and then 6 or so AJAX requests. And then the last thing on the page there, highlighted in red, is just the actual body content, which is the 5,000 shuffled numbers. So this is what I've used as the baseline. Now let's take a look at how I deployed this and where we're doing some testing from. So I deployed this to an EC2 instance in Virginia. And I had testers in Virginia, Oregon, and Tokyo. The origin itself is running the Python Flask framework, and it's deployed through UWSGI. And the testers, I used Selenium, which is a browser automation tool. And I wrote a script in Python to basically make 20 requests for this page load, for this particular page, and I'm using Firefox as the browser. So I really wanted to not make individual requests for content, because that's not what your end users are doing, right? They're requesting whole pages, and we want to take a look at how we can optimize whole pages, not individual requests. So this is the method that I came up with to do that. A little bit more about Selenium, or how I configured it. So it's important to take a browser cache out of the picture for this testing. So I wanted to show you this in case you do want to repeat these experiments. So to do that, you can see the settings here that you would need to implement. And this makes it so that there's no browser caching at all. We're really relying on the edge cache. Browser caches are an incredibly important part of performance optimization. But to kind of get numbers around what it would look like for multiple testers in the same geography, I had to take that out of the picture. All right, so let's take a look at some baseline metrics here. I have this page with 108 objects, and I'm hitting it from these 3 locations. If we look at Virginia, which is right next to the origin, right? No latency at all. We'll see the average page load time right about 400 milliseconds, 0.4 seconds. If we look at Oregon, the average page load time jumps way up to 3.4 seconds. That's an incredible jump, right? If some of you aren't aware, the ping time, the round-trip ping time between Virginia and Oregon is 70 milliseconds or so, right? For a 70 millisecond ping time, we get an extra 3 seconds of page load time. Why is that? That's something that we really need to dive into and see what we can do to fix that. If we go all the way to Tokyo, average page load time of about 9.6 seconds. Same testers, exact same configuration, but you can see that the impact of latency is incredibly dramatic. And here in Tokyo, the ping time is, again, roughly about 250 milliseconds between Virginia and Tokyo. So just keep those things in mind. What did it take a look at a waterfall graph from Tokyo to see what it would look like when you're requesting this content or doing a page load. And there's one anomaly I really wanted to point out. That's why I'm showing this graph here. If you look at 0001.gif, you'll see an awfully long connecting line. The orange part of the waterfall graph is how long the connection time is. And you'll see this sprinkled throughout the page. I can't show all 108 objects loading. This is small enough to see, hard enough to see, I'm sure, for all of you as it is. But you would see this kind of thing sprinkled throughout the page load. And that really kills the performance. This is part of why it's taking 9.5 seconds to load, because there are a number of objects that just, for whatever reason, seem to take an awfully long time to load. So this is just an observation for right now. We'll talk a little bit more about it as we go on. All right, so the first optimization number 1, let's leverage Amazon CloudFront for static content caching. Take advantage of all the things that Prasad talked about that we've worked on over the years. All right, so if we do that, the first thing I want to show you in all of the 5 optimizations I'm going to talk through is graphs. What are the improvements? And I want to do this so that you can decide whether or not you're going to care about what I'm going to say for the next couple of slides. So if we look at Oregon and Tokyo here, I'm not going to show Virginia pretty much anymore for the rest of the presentation, since latency isn't an issue there. But if we look at Oregon and Virginia, we can see that just by adding CloudFront as a static content cache, we lowered the average page load time from 3.4 seconds down to probably about 900 milliseconds for Oregon, and then in Tokyo, roughly 10 seconds there, down to about 1.5 seconds. So huge, huge improvement. So I'm hopeful that this is one of the optimizations that you really will care about. And now if we look at the waterfall graph from Tokyo again of an initial load, which means a cache miss, one thing you'll see is there's none of those big spikes. There's none of those anomalous kind of 2, 3, 4 second connection times. And a lot of that has to do with how we're, the routing that we're doing with CloudFront and the HTTP kind of optimizations, which we'll get into again a little later. But I just wanted to show you that this kind of wiped out that one particular problem that we saw. And then if you look in the case of a cache hit, this is what you really love to see, right? Nice little tiny lines on all the static assets, right? A couple of milliseconds is all it takes because the end users are very close to the edge locations. All right, so how did I implement this in my simple little application? It was quite a trivial change. All I had to do was have users continue to hit the origin as they would directly, which I have down there as a nav URL of PFC303.origin. And then in my code for the static content, instead of having a relative path to static slash, I have now an absolute path to the CloudFront distribution. So I'm not going to go through the setup of CloudFront. That's something that you can read in the docs. But it's a very simple change in the code to make this real. And the other thing that I did is at the bottom, you can see there, I added cache control headers. So the cache control header says how long these objects are going to live in the cache. So this is saying 300 seconds. So these are the kinds of changes that you would have to make in your application, or that you may make in your application to leverage CloudFront for static content caching. And so why does this really help? Well, I'm going to go through this really quick, but if you have an end user in Tokyo, they make a request for content, you're going to get routed to the nearest edge location from a latency perspective. Let's say that's only a few milliseconds away, round trip time, 10 milliseconds, 20 milliseconds is probably typical. The edge location is then going to make a request to the origin. This may be hundreds of milliseconds here, and then the origin's going to respond with the object. And the second the bits start hitting the edge location, they're going to get streamed to the end user. So that's what the case of a cache miss is going to look like. If we look at a cache hit, on the other hand, the user's going to make a request for content. The edge location is going to say, I have that in my cache. I don't need to make that long haul trip back to the origin, and can send it directly to the end user. So cutting out hundreds of milliseconds. So this is clearly very beneficial for you, if you could take advantage of it. The next optimization I want to talk about is about caching API calls and proxying your whole site. First off, we're going to start with looking at the numbers. Does this matter? And if you look at now, this first graph is just showing you Oregon. Or first a slide is showing you Oregon. So on the left, we're taking a look at what the first couple of hits look like in terms of time. And then on the right, we're taking a look at the next 17 requests. And I had to do that so that you can actually see the impacts on the right-hand side, or else the scale would be completely off. So if we look at the left, we'll see that we shaved off a few hundred milliseconds, which is definitely worthwhile. And then on the right, we have a much smoother line in terms of performance. Instead of jumping around between 600 and over a second of page load time, we have a pretty smooth line right around 600 or 620 milliseconds. So definitely, I think, worthwhile digging into. If we look at Tokyo, we'll see the exact same kind of pattern. So why can we do this? Well, many API calls, most people think of them as dynamic content, and they don't think about caching them. Well, very oftentimes you can cache them, right? And if we look at the health and beauty page, you may not be able to see those words there, but it says bestsellers in beauty. That might be the kind of thing that you're loading in via an AJAX request. And then it says updated hourly. Do your customers really need to see the bestsellers in beauty every 3 seconds, right? It's probably not going to change that much every 3 seconds. You might not want to compute it every 3 seconds. So this is clearly something that you can cache. Many API calls fall into this umbrella. And caching doesn't have to be in the order of hours or minutes. It could be seconds to take a big benefit. If you have a flash crowd that's coming in 1,000 requests a second, instead of having 1,000 requests go back to your origin, again, which is a couple of hundred milliseconds away, all it has to be is 1. Right? So you can get a big advantage there. So what does the code look like? Very simple in my application here. Since I'm actually having end users go directly to the CloudFront now, I'm going to go back to a relative path for my static assets, and then CloudFront is going to point to the origin. And I'm going to set cache control headers so that the root object is going to have a cache control header of 0, which means it's not going to be cached at all. And any AJAX requests are going to have a cache control header of 300, which means that they're going to be cached for 300 seconds. The other thing that I had to change was in my add headers to all other objects, I want to exclude the root objects, any HTML requests, any HTML responses. So that's the simple changes I had to make. want to explain a little bit more about cache control headers, and then we'll take a look at how this works. So there's there's many directives that you can have in the cache control header, but the two that I really want to point out to you are max age and smax age. So max age, if no smax age is specified, max age is going to tell you how long this object should live either in a proxy cache like CloudFront or in a browser cache. If you specify both a max age and an smax age is going to say how long this object should live in CloudFront in this case. And max age is going to specify how long it should live in a browser cache. So this is very important to understand. You may want to have a 0 for max age and an smax age of 300. That's one thing you might want to do if you want to take out the variability associated with maybe browser caches. But again, browser caches are important. So I just want to make sure that's something that you're aware of. All right, so how does this work? Why are you getting some benefits from the whole site proxying, right? We saw that the initial page load was less. There's no benefit of caching on that first page load, so why was that less? One of the main reasons is through keep alive connections with CloudFront. So TCP runs on idea of connections, right? It's a connection-based protocol, and every HTTP connection has this idea of a handshake. And so if we look at what a request for content looks like for two users, two separate users, they're both going to have to do 2 round trips to get, at an absolute minimum, to be able to get content. 1 round trip to do the handshake, which is the synchronized acknowledgement, and then the acknowledgement of the synchronized from the server. Finally, there's the request for the object, right? And the last ACK and the request for the object can happen in parallel. So the minimum time to get that object back with 100 millisecond round trip time is 200 milliseconds. You can't do it any faster than that. 200 milliseconds is the best that you can do from TCP, with the TCP protocol to get an object back with a 100 millisecond round trip time. If you put CloudFront in the middle, and again, let's assume that CloudFront is 20 milliseconds away from the end user and the origin is 80 milliseconds away from CloudFront, you'll see on the first user, which is the top part of this graph, it's exactly the same, 200 milliseconds. But on the second user, it's only 120 milliseconds because we can shave off that handshake between CloudFront and the origin because we will very likely have a connection kept alive and basically a connection cache you can think of at that edge location. So you can see this, 80 milliseconds is important, right? We can shave that off, might as well. Another thing is window size optimizations. Here, basically a server is going to send a certain number of packets to an end user before it has to be acknowledged. And so this is showing you the progression of that. Basically, the window size is going to expand until you've met the maximum capabilities of the quality of service of your connection. That has to get done every time that you establish a new connection. But if you have that connection kept alive, the information about the quality of service of that connection can also be kept alive, right? So the window size between CloudFront and your origin can be fixed and is likely going to be pretty large since we have incredible pipes coming out of CloudFront. All right, so the next optimization I want to talk about is a multi-region deployment. So here we're going to look actually at a map first. What I did is deploy a second origin in Singapore. And we have the same 3 test instances. And so let's look at the numbers now. I'm only going to show you for Tokyo because that's the only place this is going to matter. Oregon's going to still go to Virginia. So Tokyo now will hit Singapore for its origin. And you could see, the initial load is going to be, the first hit is going to be significantly less, right? From 8 seconds down to 4 seconds. So definitely worth doing. This is, for me, in this simple application, an incredibly trivial thing to do. All I had to do was stand up another instance. There's no code changes at all required. For you, it may be much more complicated. So, this may or may not be something that you can do. The complications really come into data synchronization. If you're running a database, right, how are you going to get data in both places at the same time? So that's that's a difficult challenge to solve. But in this simple application, it's very easy. And one of the ways that we do that is through the latency-based routing capabilities of Route 53, which is our DNS service. So this is going to allow you to run multiple origins in different regions and pick the origin that you're going to go to via latency-based routing. So let's look at what that looks like from a map perspective. So if we have the testers in Oregon and Tokyo making a request for content that's going to get resolved by DNS, which is that shield there, to CloudFront, the nearest edge location, right? So probably something very close by. CloudFront is then going to make a request to the origin, to the DNS name for the origin. That's going to get resolved by Route 53 to the nearest origin, right? So you can see here how the CloudFront edge locations for Oregon would end up in Virginia, and the one for Tokyo would end up in Singapore. All right, so the next optimization I want to talk to is flipping optimization 3 on its head, which is cache the base page, but make the API calls, the AJAX calls, more dynamic. Right? Let them take care of the dynamic stuff, but cache the base page. So looking at the numbers, does this matter? On the first hit, really no difference. And this makes perfect sense now because we've already gone through proxying the whole site. We're not getting any benefit out of caching here. So first hit is a wash. But if we look at subsequent requests, we can see a decent improvement in performance, probably a little less than 100 milliseconds improvement in performance. If we look at Tokyo, same kind of pattern, right? No improvement on the left side, but decent improvement on the right. So why does this matter? Well, there's 108 objects to load. One object is the base page. That base page is blocking everything else, right? Until we start getting the bytes of the base page, we don't know what the other 107 objects are to load, right? So the more we can do to accelerate that, the better we are overall, right? We can start doing things in parallel, right, which is the key to performance. So that's what this waterfall is showing here. And from my application, all I had to do was flip what I'm doing with the cache control headers, set the max age on the root object to be 300 seconds, and on the AJAX calls, I can leave that at 0, and that's it. But for you guys, it's probably going to be a little bit more complex. So let me give you some ideas on how you can make this a reality for you. So what are some of the types of things that you may want to do on the base page? You might want to determine what the browser is, so you can serve a mobile version versus a desktop version. And CloudFront is going to, what it can do for you, if you choose to do that, is have it inject a header to say, is the viewer a mobile viewer, a tablet, or a desktop viewer? So you can vary the cache based on those headers. So this is something that, one of the things that you can get out of it. What language is the viewer? You can, again, vary it by the accept language header. And then from a personalization perspective, let's say it's me, John Mancuso, logging into the Amazon Health and Beauty site. I might want to see what my product recommendations are. I can do that via an AJAX request, right? I don't need to get that from the base page. I can make an AJAX request to say, all right, these are the personalized items for John. But how am I going to handle the authentication? Well, you can definitely see a push over the last few years for both the end users' benefit and your benefit as a site owner to use web identity providers like login with Facebook, login with Amazon, Google. So those can basically, whether the person is logged in or not can be persisted in JavaScript. It doesn't have to be part of the base page logic. So it is doable to do that, and I think you can saw it was a pretty good benefit. The last thing I want to talk about is about optimizing for browser behavior. What does this mean? This is actually a bundle of optimizations. I'm going to get to them in a second, but let's see if they're significant or not. So if we look here for Oregon, we see that we can save over a second, well over a second on that first page load. So definitely worthwhile there. And then on the right-hand side, you can see, again, a decent amount of time saved. So I think this is really important optimizations that you guys would want to take advantage of. Tokyo, same kind of thing. So what are they? What is this bundle of optimizations that I went through? So first off, instead of having one alias to CloudFront, one CNAME, it could be mysite.com, I'm going to have multiple. So I'll have mysite.com, mysite1.com, mysite2.com, mysite3.com. And I'm going to use them strategically, and I'll explain why that matters in a second, but right now I just want to tell you that's what I did. Reduce the number of objects in the head requests, because just like the main page, the rest of the body objects can't start loading until the head is done loading. So anything we could do to accelerate that is a big benefit. We did that by combining all the CSSs into one file and all the JavaScripts into one file, and just only making 2 requests in the head. So that's something that anybody can do, right? There's usually not a big blocker to that. The next thing is enabling gzip, right? So compressing all the content as it gets sent will help. And then it decided to initiate asynchronous calls early on in the page load lifecycle. So let's take a look at why I came up with these ideas. And to do that, we'll look at this waterfall graph. So if you're looking at the waterfall graph, and I apologize, I know probably it's going to be hard to see, but it's something you can always come back to on the video afterwards. If you look at 001.gif, which is the first part of the body, you can see again, just like I said, that has to wait for everything in the head to load, all the CSS files and the JavaScript files. And then a really interesting thing is look at where the orange line starts to build, right? If you look at 006.css, you'll see the orange line starting to build. So that's the connection time we talked about earlier. I'm not going to answer that for you right now. Maybe some of you know the answer as to why that is. I'll answer it in the next slide. But right now, let's just observe that. And the last thing is the AJAX requests. We can see that they don't start loading. I had them at the end of the page just by chance. And they don't start loading until every other object has been loaded, right? And now we have to wait for the page to load for an asynchronous thing. You really don't want that to happen, right? So initiate these asynchronous calls early on, and then the rest of the page can continue to load while they're happening. So this is the reason for that 6, right? Why did the connection time start building on 006.css? It's because typically browsers have a setting that says how many persistent connections can be established from the browser to a server. In this case, it's 6 for Firefox. It used to be 2. It depends on the browser. It depends on lots of things. So this number isn't like always going to be 6. But I wanted to make sure that you understand that there is a limit of how many connections that a browser is going to make to your server. And if you have 108 objects, it's something to keep in mind. All right, so let's look at the post-optimization benefits. So the first 3 requests, the body, the CSS file, and the JS file, are all happening through one domain name, PFC303.cdn.jman.ws. So I'm not using any other alias yet. And you can see that we've gotten those done a lot quicker than we had on the previous waterfall. That connection time for 006 doesn't start blocking until way down in the body load. So the next couple of requests, which are the AJAX requests, we're using a different alias now. It's PFC303.cdn2.jman.ws. And so we don't run into that 6 connection limit. We've not made 6 requests yet before we started processing the AJAX requests. And these requests are now not going to block anything else because they can all happen. There's 6 requests, 6 connections possible from PFC303 CDN2 and PFC303 CDN3 all to the server. So they're going to all happen without any kind of blocking. The first time that we're going to get a connection blocking is, like I said, way down in the body load. You can't make 108 simultaneous requests to the origin. That just probably wouldn't make sense. But the important thing here to understand is that you can use multiple domain names to basically strategically place where the connections are going to get blocked, right? Where it is that you're going to have asynchronous requests go without blocking other requests. And then you can see the benefits of compression and so on. So those are the optimizations I wanted to walk through. Let's see the summary here in terms of what percentage improvements we got by going through these 5 optimizations. For Virginia, that last one, optimization 5, it's more than just fighting latency, right? This is making your whole application faster even without any latency. You can see that really had an impact by 11% and 27% roughly respectively for the first request and subsequent requests. At Oregon, 31% and 86% savings for cache hits. right? I mean, that's an incredible number. And then Tokyo, again, 76 and 95%, 96% really. Now, I know many of you won't be able to do multiple origins, like I said, so I wanted to show you without that one optimization, without the multiple regions optimization, we're still looking at 52% improvement in page load time in Tokyo and 93% for cache hits. So that's all I have. I want to just call out a couple of things. You know, we're short on time here, so we may not be able to take many questions. If you have questions, you know, we'll stand over here to the side and try and answer as many as we can. But you can go down to the CloudFront booth, or in the AWS booth, there's a CloudFront section. We're happy to take questions there. Also, there's a webinar coming up next Thursday on reporting on CloudFront, which is an important part of performance optimization as well, just knowing how your application is doing. So if you want to join that, it would be great. Thank you, and please give us feedback on how we did.